This is the Convergent Science Network podcast. Leading researchers in the domain of neuroscience, brain theory, and technology are interviewed by Paul Verschure and Tony Prescott.
This is Paul Verschure with the Convergent Science Network podcast. And in this episode, I'm speaking with Giovanni Pezzulo, who is a speaker at our summer school, Barcelona Cognition, Brain and Technology Summer School. And Giovanni, you started out with investigating this whole issue of the predictive brain.
Yes.
Right? So what does it mean for you, a predictive brain, exactly?
Well, in a sense, the predictive brain is just a big idea. Well, the idea is that the brain is not a passive organ. So rather than just sitting down and waiting for the next stimulus, in a sense, it really always tries to anticipate what comes next, to set up some internal goals, and so to have some big internal processing. So rather than being stimulus-based, it's really trying to anticipate the necessities or maybe the opportunities for action. So that's really the big principle that drives all the brain processing. Because the brain has some predictions, some goals, it can really organize its sensory processing, its attention processes, and its motor preparation processes for quickly responding and doing some adaptive actions. So to do that, it has to be predictive and proactive.
Mm-hmm. So, but then where does that really start? What are the good examples of this kind of prediction?
Well, in the literature, there are many partially disconnected literature on prediction. So predictions in sensory processing, predictions in the motor domain, predictions also in higher cognition, in that, for instance, I can try to anticipate what your next question will be. So all these literatures can now proceed a little bit disconnected. But for instance, in the sensory domain, you see a lot of predictive stuff going on, such as the anticipation of the next stimulus. In the motor control domain, you really have to get rid of what are the consequences of your action. For many reasons. One big reason in the motor domain is that sensory perception, they're very ambiguous. So by also predicting what comes next, you better estimate the state of the world. Another big reason is for decision making. So if you can really anticipate what the effects of your action are, then you can also select among different courses of actions beforehand. So such as, for instance, if I anticipate that by going left, I will get some big reward, and by going right, I will get some big punishment, then that's the decision.
Mm-hmm. But now, in some sense, let's say also the physiological study of learning that started with Pavlov, one of the first observations of Pavlov was that the brain is predicting, right? So
yes,
that's also a key feature of classical conditioning. So in some sense, the concept of prediction is with us for a long time. Indeed, as some speakers have said, like sometimes certain things get so old that they sound new again, right? So, so what is actually really new in this current movement of the brain as a predictor?
Well, actually, I completely agree that also in classical conditioning, you have this predicting dynamics going on. But I think that we should try to really distinguish at least two kinds of predictions. Well, it's not a sharp distinction, but it's useful to do probably. So one is an implicit kind of prediction. In that, for instance, in the conditioning studies, so a stimulus, which is typically highly predictive of another stimulus, which is in turn highly predictive of reward. So the first stimulus, which is predictive of another stimulus, it becomes itself good to achieve. So in that case, the brain becomes implicitly predictive, in that it stores the relationships between the first and the second stimulus. But to do that, you don't really need to maintain into your memory or to an internal representation of the predictive relation between the two stimuli. You just attach some good label to the first stimulus.
Mm.
Whereas there is a second kind of prediction, which is a more explicit prediction, in which you keep into your brain some model of the environment. So the point is that in the first case, you really have some implicit mechanism that link good or bad to sequences of things. Whereas in the second mechanism, you also maintain a model of these sequences of things. So you for instance, in the motor domain, you can, for instance, let's say you have to grasp a moving ball. there are two different ways to do that. So one way is to look at the moving ball and then jump to some future state that the ball will reach at some point. This can be done in two ways. The first way is just learning the contingencies automatically. So I know that if I see the ball moving, then I have to go to some position, which is not the current position, but the future position. Without even anticipating that position explicitly, you can do that automatically. The second way to do that is really doing what is called a forward model. So a predictive model that really tells you where the ball will be in the future. Use this forward model online, so this predictive mechanism online, and then move the hand to the predicted position. So to recapitulate this idea, there are implicit and explicit mechanisms, and the novelty of the predictive brain hypothesis, if you want, is the hypothesis that the brain systematically incorporates regularities of the external environment in a structured way so as to form strong models, statistical models, for instance, of the regularities of the external environment. And then it systematically uses these models to plan what to do next, and also to drive perception, to drive attention, and so on. So, whereas in the first formulation of prediction, it was more an implicit prediction. In the predictive brain hypothesis, at least in some of its formulation, it's much more about building models of the world, on top of which you can run explicit predictions.
Right. So then, if you would look at, let's say, the theoretical literature on the predictive brain, what in your mind are right now then, let's be the outstanding examples of this approach?
Well, there are many of them. So probably in a very famous paper by Rao and Ballard, it was already in 1999, if I remember well, it was about this predictive coding idea in perception. So the idea is that the brain continuously generates prediction about the stimulus, and it uses these predictions in a top-down manner, whereas it uses prediction errors, so the difference between the prediction and the sensory evidence, as a revision mechanism. So that was a milestone in a sense. But, well, there are many other papers. Now there is a very big framework put forward by Carl Friston, which is called the free energy framework, or the active inference framework. In that sense, Friston really tries to look at the whole brain, not just the perceptual system, as a big prediction machine. There are many other frameworks. One is put forward by Moshe Bar, again in the perceptual domain. Whereas in the motor domain, also the leading view, one of the most authoritative view put forward by people such as Danny Wolpert or by Shadmer or many other people, is that you, in reality, what you really predict is the sensory consequences of your actions. So that framework is more tied to motor predictions. Other people such as Marc Charot or others, they have tried to expand this framework from the prediction of the sensory consequences of actions to more complicated forms of cognition, such as reusing this prediction for understanding of the action of others, such as reusing this prediction for imagery, and so thinking at more abstract situations. So I would say that there are many fields in which prediction have been studied, and also some converging frameworks.
Right. So now, if we talk about your own experiments in let's say the role of prediction in problem solving, you show some examples of what you called embodied problem solving.
Yes.
Right. So how does that, which aspects of the predictive brain are these experiments exercising? Well,
it's not so simple to explain the videos that I've shown. But just to recap, it's just a video of a climber, and maybe you know, but climbers prior to a competition, they have some time to look at the climbing wall that they will then climb during the competition. The nice point is that they see this climbing wall for the first time, and there are in these climbing walls, there are many climbing holes arranged all through the wall, and the climber has 1 minute or a few minutes for figuring out how to better climb this wall. And if you look at the video, or if you look at a climbing competition, you see climbers really moving the arms such as to really anticipate the next moves. They see moving the arms in one direction, then the other direction. That's really a form of problem solving, because they see the climbing wall for the first time. They have to figure out a good plan for action. I call it problem solving, not only planning, because it's really complex. There are many constraints. It depends on where you go. Then you can reach or cannot reach the other hold. So you can also find in your mind many solutions, compare them. And in this specific kind of setups, the hypothesis is that it is really the motor system that is governing this process. So expert climbers are really able to anticipate the force they have to put into this motor act. They can really anticipate a lot of proprioceptive information. They can really figure out if a hold is in their reach or out of reach, if this hold is too little to be really grasped. If it is too far away for them, then they have to take another route. So that's, I call it embodied problem solving for many reasons. So one reason is that you really use knowledge of your body and of your motor system to figure out how to better solve this problem. And another reason is that it's also overtly embodied, in that you really use your body movements as a scaffold, as a helping tool for solving the problem. That's a bit tricky to explain without the video, but in a sense, by simply moving yourself, you don't need to keep everything into your memory. You use your body as part of the problem-solving process.
Mm-hmm. Okay, but now you could also see it as a form of, let's say, motor programming. That you say, look, I have to execute a movement sequence very rapidly, and I'm just going to now rehearse this movement sequence so that I can sort of automatically trigger one set of behavioral or motor patterns after the other, and I can climb up the wall more rapidly.
Yeah, that's part of the story. So the point is forming this motor program. Mm-hmm. The reason why I call it an embodied problem solving is that the solution is not so trivial. So the point is that you have to try to form this motor program by assembling partial skills that you used in the past in novel ways. So there is a lot of flexibility in this new assemblage of motor or small motor programs.
Yeah, but the problem solving would suggest that there is also, let's say, a goal state in the world that you want to achieve. In order to that, you also have to manipulate aspects of that world.
Yeah.
Well, in this case, it's essentially making sure your body goes through a certain sequence of motions. So how would your view on embodied problem solving then generalize to problem solving in general? Because I would assume that you want to identify some more, let's say, generic aspects of problem solving as opposed to specialized aspects of problem solving.
Yeah, okay. So there are two parts of this story. So one part is that even in that case, even in this climbing example, you have a goal. So the goal is reaching the top. And then it is not simply running through a trajectory, but also finding out which is the good trajectory. So it's not so different from the Tower of London or other typical problem-solving setups. So you have a goal state, and you have many sequences of moves that you can do, and you explore this space of possibilities. But the trick is that you explore it in intelligent ways. So you don't simply try out all of them. You really use your expertise to find out how to better explore this. The second point is that you really use knowledge incorporated into your body, your motor programs, to figure out what are the constraints of the problem. So the climbing problem has many constraints because, as I said before, if you are too much to the left of the climbing wall, you cannot reach anymore the holds on the right, or vice versa. If you jump too high, you cannot probably make your body stiff enough to really hold the climbing hold. So there are many constraints that you really discover while solving the problem by reenacting this motor knowledge. That's my point. And the second part of the answer was about how much this generalizes to more complex and abstract problem solving. So, well, first of all, this is just a nice video that I showed just for illustrating the possibility of solving problems by reusing more motor knowledge or sensory motor knowledge. It could also be affective knowledge, so knowledge incorporated into the same models that you use for acting in the external world. Mm-hmm. So I think that as a general strategy, that's the way we should look at higher cognition. So the challenge is looking at how you solve higher cognitive skills, such as problem solving in abstract domains, by reusing these strategies that you acquired so as to efficiently deal with the external environment. Mm-hmm. So when you have these sensorimotor strategies, then probably our earlier ancient evolutionary ancestors, they had only these simple strategies to deal with their current situations, whereas higher cognitive skills is mostly about very complex abstract situation, non-perceptually available events, distal goals. But the challenge is seeing how simple strategies that we used in the past to survive in the environment can be sophisticated and reused in these more complex cognitive domains. So that's a challenge. My example was just to illustrate the possibility that you can really solve problems by reusing systematically knowledge incorporated into your internal models in an intelligent way. And that allows also for a lot of flexibility. It's not for planning the next action, but also for solving very complex problems.
Yes, yeah, but that's a bit the wish, right? That's the wish. And
yes.
Then the question is, how far are you in realizing that wish? Because first in the climber case, do you see a big difference between expert and novice climbers?
Yeah, absolutely. Yes. Mm-hmm. So part of the story, which is also one of the reasons why I'm interested in it, is that in a sense it is the expertise that not only modulates the climbing ability, but also the ability to think about problems. Mm-hmm. That's supporting for the embodied cognition view, or for the view that it's really knowledge incorporated into your motor system that helps you not only in executing the actions, but also, for instance, in imagining the actions, in reusing the repertoire for solving problems. At the same time, we have evidence that knowledge incorporated in your motor system also helps you understanding what other people is doing.
Right.
So that's the idea in a sense.
Yeah, that's in the step into the social cognition component. But in some sense, what you're saying, look, the standard view would be, let's say we perceive the world, we have some sort of high fidelity in the end interpretation of the world on the basis of which we make decisions and perform action. But now the consequence of what you're saying is that, look, I'm actually acting in this world, and the way I act in the world is now modulating or directly filtering the way I'm going to perceive this world.
Absolutely.
So the processing goes backwards in that sense. So the expert climbing is looking at this world very differently as the novice climber.
Yes.
And you have evidence for that.
We performed them. Of course, we have tiny evidence up to now, but I think this evidence points in the right direction. So one memory study that we performed comparing novice and expert climbers. So we simply asked to these novice and expert climbers to look at at 3 climbing routes, one simple that both of them were able to execute, one difficult that only the expert group was able to do, and one impossible, which was not climbable actually. It was not really a climbing route. It was just a random displacement of climbing holds. And so the task was simply remembering the climbing holds in the right sequence. What we found is that in the easy condition that both novice and expert were able to climb, both were also able to remember quite well. So there was no evidence for a better remembering for experts. While for the difficult route, only the experts were really able to remember it well, and this. In our opinion, this points to the fact that really the way experts structure perceptually also the situation can also help in this memory task. Mm-hmm. And so we had this control condition in which for the impossible route, in that route we did not find any advantage for the experts because this increased memory ability is really tied to the climbability of the wall. It's not a generic ability to remember climbing holds without context. But to respond completely to your question, I would say that this sensorimotor approach, so this sensorimotor influence of thinking on cognition, to me at least, it acts on at least two time scales. One time scale is learning and development. So the point is that because I have some sensorimotor skills, then I change the way I perceive the world. So I structure my memory and my perceptual abilities in such a way that then supports better cognitive abilities. So that's acts on a longer time scale of learning and development. The second way the sensorimotor system supports cognition is more in the online cognition. Because I can reenact my motor problems right now, my motor programs right now, so I can use them so as to support, for instance, imagery or action perception. So there are two sides of the same coin. So in a sense, this framework predicts that if you increase your sensorimotor abilities in one domain, then you really shape your perception, your memory, and all your cognitive processing. And then you are also better able to run imaginary experiments based on this motor expertise that you can now reenact.
Right. But then would the expert climbers recognize the unclimbable wall more rapidly than the novice climbers?
Well, probably, if the task is exactly recognize whether or not it is climbable or unclimbable, that's the task. If this is the task, well, of course, this is a bit of a tricky task because unclimbable is not such a clear concept. But anyway, yes, I would say that in that case, what will happen is just that the climbers try to climb it mentally. So they run this imaginary climbing simulation. And then because the expert will anticipate some failure in climbing, because they have high confidence in their internal models, they will say, no, this cannot be climbed. Whereas for the novices, maybe they will try out to anticipate. They will also fail, but without noticing without trusting too much their simulations. So that will be my...
Right. But now, still a problem for this point of view is that you could say, look, the climber is a highly specialized human being. So it's not very surprising that they have certain cognitive capabilities because they have been overtrained in dealing with certain kinds of environments like climbing walls. So how would you see this sort of but you want to look at this as an example where you say, well, it's actually very basic sensory motor patterns, or it's really action itself and the way we generate action from which the rest of cognition is sort of bootstrapped or is depends upon, is constrained by.
Yeah, that's exactly.
So how is it going to work exactly? How do you see that work?
Well, I would say that now we don't have any perfect story yet. But the point is really that action and the goals implied in the action and the predictions implied in the action, they are really key to cognition and to develop increasingly more complex cognitive skills. So at the beginning, that could be a simple story. So at the beginning, the brain is simply organized around these goal selection and specification and selection tasks. So they have to integrate information from the external world, from the memory, from affective states to very, very quickly jump into a good action selection. And to do that, as I was told before, you mostly rely into your internally generated goal state, affective processes, attentional processes. The stimulus help you, but then it's the brain, which is autonomous, is doing the job. But then, as the sensorimotor abilities of this primitive architecture develop over time and increase your abilities, they increase their ability to control the external world and to predict it. So they start incorporating more and more knowledge, more and more also structure from the external environment into their predictions, into their motor control actions.
Right. So how are you going to validate this prediction? Is it a pure experimental exercise, or are there other ways to get this validated?
The framework, you mean?
Yeah.
Well, the framework, that's much more a lifelong research program, if you want, because we are trying to do many validations. A few empirical data, of course, already exist. If you think at the literature of how similar the brain networks for imagery and for execution or for motor preparation they are, so you already see that some mental operations are really supported by the sensorimotor system in the brain. So that's some evidence. There is evidence. Well, there are also patient studies that say that in some conditions, the imagined action cannot be really stopped from being overtly executed. So that's another part of the story, because in this story, it is the internalization of the predictive mechanism that really supports cognition. So you first predict things in the external world, then you internalize this capability of predicting, and this eventually leads you to rehearsing entire sequences of action without executing them. But then a prediction of this framework is that if you really do this covert mental imagery, if you want, or this covert predictive mechanism, and you cannot really separate these internal processes from the overt execution, then this implies that what you imagine you immediately do.
Right.
And there is evidence that this unfortunately happens in patients with bilateral parietal lesions. And other evidence of this close connection between what you think and what you do also exists for utilization behavior. For instance, utilization behavior patients, they are not really able to inhibit their motor programs for grasping objects and just reacting in a very quick way to what they say. So this tells a story on how this more abstract thinking part is tied to the sensorimotor programs.
Okay, but now this in how do you what's the role of this the internal simulation in that case? Because on the one hand you're saying, well, we run these internal simulations. Apparently they would run in parallel because, but on the other hand, if you look at the deficits that you mentioned in these patients, it's not that they are executing a whole sequence of actions in parallel, right? In the utilization behavior, you would grasp a single object and the whole organism will be focused on that. So can we really is this kind of evidence coming more from the clinic, from clinical studies, really supporting this hypothesis of internal simulation and the role of action in the structure of cognition?
Well, for the first evidence I mentioned of the patient who was unable to inhibit the imagined action, that's quite clear, the link, because then what you think is what you do. So if you imagine, let's say, pointing to one direction, then you point in that direction, you cannot really stop from doing that. So in this framework that I'm supporting, the idea is that you run this imaginary simulation of pointing. And this is typically done by also inhibiting the overt motor execution. But if you have a deficit, you cannot inhibit that output. It rapidly turns out into an overt action. In the utilization behavior, the link is tiny in a sense. The idea is that one idea in the literature of affordances, also the canonical neurons literature, is that when you look an object, then you automatically, let's say, prepotentiate some motor programs that are good for interacting with that object. Okay, but typically this does not result into an overt execution. So in a sense, this is just a prepotentiation, which can be also interpreted in terms of simulating grasping this cup in front of me. So in that case, I'm not reasoning about simulating the action. This is just a more automatic process of mentally rehearsing of the good action that I can do. Again, if you don't have let's say, this mechanism working well, you cannot really inhibit also the overt execution. I would say that while in my first example of the imaginary situation, the link is clearer, in this second example is less clear, but to me, it's another supporting example that your internal mental process is always oriented toward anticipating possibilities for action. In some cases, this is just a simple automatic process that tells you what is possible to do. In other cases, this is more intentional imagery. So you really run long-term simulation imaging sequences of actions. But I see a continuity in this. So the good thing about this framework is that you do not have to postulate any different set of cognitive representation for different tasks, any module for thinking that is completely segregated from the action, control, and specification, but you have a continuum reuse of the same abilities in more complex ways.
Okay, but then would you see this as being, let's say, layered in some way, that you have, let's say, sensorimotor capabilities of, let's say, varying levels of complexity with some sort of discrete steps between them? or it's really a continuum?
Well, that's a hard question. One important thing in this framework that probably answers partially to your question is that we have to probably focus, we have to talk about actions as the unity. And also, we know that action can be specified at different levels of detail. So there are actions that are specified at the level of movement of a single finger, whereas there are other actions in which the action, but also the goal of the action is specified at a more abstract level, that is grasping this object, this cup. Whereas there is still another level of action and intention associated, which is, let's say, drinking from this cup. So the actions, all these levels are in a sense they support one another. Sense. So, of course, the more abstract actions have to be finally specified in more fine-grained terms of the movements of the fingers. Mm-hmm. But this is a structure, a cognitive structure that has different layers, probably, or we don't know exactly. But at least you have a big structure in which you can really specify actions at different levels of complexity, a different level of abstraction with more complex intentions. And the arguments that we do is not that we always use the lowest level, the lowest possible levels. At some point, you can really think and do some imagery by using actions and their associated intentions at intermediate or even at abstract levels. So that's probably answers.
Right. So now one way to test some of these ideas, you were performing and presenting experiments on joint action.
Yes.
Right. So how does joint action now help you to understand this model of cognition and action in the end?
Well, the reason why I went into joint action in my presentation is that, as I told before, I would like to come out with a convincing story or more complex cognitive abilities developed based on simpler cognitive abilities. So here the steps that I presented are, okay, I start doing my action. But then I'm in a social domain, and so maybe I need to do some action together with you. So in this case, I can reuse a lot of what I know about my action system to anticipate you and to get into your intentions. So to get rid of your motor system or your motor action of your intentions. In this case, this is just the beginning of a story in which I reuse my sensorimotor knowledge or my action execution and prediction abilities to get into more and more complex situations. In this case, it is a social situation, but it could be even a non-social situation. Still another step in this passage is that, okay, now I'm able to use my predictive abilities to predict you. I use my body and my action system as a model to understand your body and your action system. And then I maybe use these abilities to plan long-term joint action. To do that, then I have planned some more coordinating actions, so I have to plan how to really achieve them in practice. I have maybe to invent some way to better coordinate with you. Mm-hmm. And maybe at some point you invent more and more complex things. You extend the boundaries of your control to the control of my body or to the control of our body or our combined actions. Mm-hmm. And maybe also to the control of your internal states, so your beliefs, your intentions. So I do some action to change your intentions. So not only I control my body, I now control me and you. And now control you. And I know that even after this interaction, you will have some new beliefs. I extend my control capabilities from myself to you. Mm-hmm. So that's the very beginning of a story in which we begin to go into more and more complex cognitive abilities, starting from simpler ones.
Right, but so for the joint action experiment, you were looking at hand movements essentially, right? You were tracking hand movements.
Mostly, yes.
Yeah? And then you also built a model of that.
Yes.
Okay. So which aspect now of the joint action control of hands do you capture in this model?
Well, if we think of the model specifically, then, in a sense, the key idea of the model is that, It's not completely new, it's not new. There are many similar models, but the idea in a sense is that I really use my own action abilities as a model to understand your action right now. So the model can predict for instance, the hand trajectory, but at the same time, it can also give some hint into your intentions and goals, because I know what are the goals that are linked to my motor actions.
How does the model know that?
Well, let's imagine I see you moving your arm towards a cup, okay? So now the hypothesis is that I run an internal simulation of the possible actions that I could be that are quite compatible with the actions that I'm seeing. I start predicting better and better your trajectory, and then let's see that this model fits quite well the data, so your hand trajectory. Because I know what is the goal of my hand action, I also can have some hypothesis of what is the goal. So because I know that my trajectory eventually reaches the cap and then grasps it, then I can also infer or at least hypothesize that you will do the same. So I also know what is your goal. Mm-hmm. That's the key idea.
But then the intentional labeling of the sequence is then with reference to your own action, or that is in reference in some way to observing the other?
So the idea of these kind of models is that you use what you know about the link between the trajectory of your arms and your goal. You know them because you execute them. You use exactly the same link to get some understanding of right. What the other is doing. So that's the idea.
So you need some sort of self-monitoring system that develops a self-model that you then generalize to the other. This would be the step.
Exactly. So I will not necessarily call it a self-monitoring, in that you simply need a forward model and an inverse model. So you need some control capabilities for yourself. And then you use this exactly as a model to understand the other. Mm-hmm. So that's more or less the key idea. And this idea is pursued by many people actually also.
Right. Mm-hmm.
Yeah.
Okay. So then, do you feel confident then that this original idea you had about this more, let's say, embodied problem solving, action as grounding, cognition, what tells you in this joint action task where you now are generalizing this model to social interaction that this is working? Because in some sense, I could also argue, well, it works because you have been imposing, you have really made the task pretty abstract, right? Because then I'm just observing these hands moving in one plane. I don't have to do anything about, let's say, invariant recognition of posture, of limbs, and so on. So to really now generalize this to, let's say, a realistic scenario where you have to observe another human moving about in space, is that just a small matter of programming, or are there some fundamental steps still missing?
Well, to answer this question, probably we have to go into a bigger picture. So the bigger picture to me is that now, although I have emphasized these motor predictions, that's not the whole story. So in a sense, my opinion is that the brain is a smart guy. So the brain always uses all the knowledge that it has, at least in principle, to do the job. So the point here is that in more realistic joint action or action observation scenarios, there is a lot of information available. There is perceptual information, which is available. There is some context information, such as, for instance, I see what are the objects within your peripersonal space. So that's my prior. I can have a lot of prior information on you. For instance, I know that you like very much the beer. Mm-hmm. So if there are in front of you see, I see some beer and I see some Coke, I would maybe anticipate that you will grasp the beer. Mm-hmm. And then I also use this motor simulation that I told, because it is also useful. So I'm not assuming that the brain only uses this motor simulation part. It uses the motor simulation to support this action understanding, because in this context, it is very salient and very useful. Mm-hmm. Why is it very useful? Because, I have a very good model of my body. So it's a very good model, very good predictive model for your movements. Of course, I have also some purely perceptual predictive mechanisms that can help me predicting you. But I would say that in the case of human understanding, the model of myself is a very, very good model of you in most cases. So this is what the brain will use the most.
Right.
But if you go into the biggest picture, you can think of it as a big Bayesian process happening. So in a Bayesian process, you basically use all the information you have. Information which comes first then can be also used as a prior to run the rest of the process. And then all the new information that is collected is fused in an intelligent way. Intelligent here means that it is weighted depending on its uncertainty. So if the motor system is a very good model, the information it provides will be used very much. If this information is not good or it is failing, then it will not be used very much.
Yeah, but you seem to now to drift away a little bit from your original proposal, because I thought you started out by saying, look, cognition is really predicated on action.
Yeah.
Right. But now you seem to say something like, well, the motor system is one of many sources of information you could consider, because the Bayesian system basically uses all the knowledge it has, and it has knowledge about the motor system, but also about, let's say, perceptual systems.
Yeah.
Or from memory. So aren't you a bit drifting now in that argument?
Well, I don't think so, because as I told before, the way you collect this information in the first place is through learning. And through learning, the motor system has really influenced you a lot. So also through learning, this perceptual information that I have acquired it by also interacting with the world. So the motor system really is used very much not only online, as I told now, but also during learning. Of course, we don't have to be radical on that. So we don't think that only the motor system does something in the brain. There are many parts of the brain that are used, and probably the point is the point is slightly different. The point is not all about the motor system. So the point is that the ability that you have to interact with the external world, which can be supported by many systems in the brain, prominently by the motor system, but by many systems. You reuse them consistently to achieve new cognitive abilities. So to develop and then to achieve new goals specified at different levels.
Okay, but so then you're saying, well, action, let's say, impregnates all other aspects of cognition and perception
through learning,
because of learning. Okay, and so it either has a direct and otherwise an indirect impact.
Yeah, there are both. I would say that the first one is through learning, the second one is during overt interaction with the external world, and then through the internalization of this action and prediction process, you can imagine new scenarios. But this doesn't mean that when you can have some motor simulation, you close your eyes, you don't use perceptual information. That would be foolish from the point of view of the brain. And there is an important point of this view is that, as you know, in action understanding, there are many views. One view is that I call this the mirrorist view, is that the first thing that is active is the recognition of the goal. Then the recognition of the goal in the mirror system, of course, it eventually helps also predicting the action. There is a second view which is related, but in some sense also very different, because this view is that what you do first is prediction. So it is prediction which comes first, and prediction helps then recognizing the goal. Still another view is that all these motor simulation things, they are not so important, because we really use much more abstract knowledge of what the other person should do, given the context. So that's more theological knowledge, if you want. Well, in the view I'm supporting, it is not so useful to say what is more used, what is less used. So what comes first can be used as a prior for the rest of the things, and what is more reliable is used more than the other things. It happens, at least to me, that this motor simulation in that specific context, they are very reliable. Mm-hmm. This is why I think they play a prominent role, not because of some categorical distinctions. And also relating to this issue of what comes first, goal recognition or prediction, that's really depending on the task. So if I have a big prior knowledge of what the most likely goals will be, then it is probable that I will force some hypothesis or some probability distribution over those goals much before starting predicting you. But if I cannot see what are the goals, let's say that the objects you can grasp, I will probably start by predicting, and by prediction I will get into some hypothesis of what is your goal. So everything can be very flexible.
Okay, but you are saying ideally you take a model-based approach towards,
Yes.
in this case, also social perception. You want to say, look,
Yes.
you want to get to the goal of the intentional state of the other agent as quickly as possible. And from there, you just reconstruct the rest of the action.
Yes, in some sense. So typically I want to go into the goal when this is useful for my task.
Mm-hmm.
So if my task is understanding which cup will you grasp, that's the goal information that I need. Whereas if I don't want to hurt you, it's more the trajectory that I want to know. So it's for instance, when we are driving, I don't really need to know where are you going.
Mm-hmm.
I don't care. I don't want to cross you or to hurt you. So it's not so much the goal of what you're doing that is important, but it is the trajectory that you are doing right now.
Mm-hmm.
Of course, also the goal is interesting because the goal tells me a lot about your trajectory. So I would say that what you ask, so what you want to infer is very much task dependent, and as a side effect, you will also infer many other things that give you useful priors or give useful hints. So that's my.
But
my
now,
view.
You don't only run experiments, right? Also to test these ideas, you also use robots.
Yes.
So how have robots helped you to make progress on these issues?
Well, yes, we are running many computational and also robotic experiments. So one thing that we have recently seen is that, probably this is very interesting again for the argument that more and more complex cognitive abilities can be developed on top of this sensorimotor interaction. One thing that we are investigating with computational models and robots is the ability to signal in social contexts. So just to explain this very quickly, the point is that if we are supposed to do one joint action, okay, let's say building some tower together, but of red and blue blocks, okay? One red, one blue, one red, one blue, okay. Now we are interacting, we are supposed to do that, and we are able to coordinate to do that. But now let's imagine only I know what is the goal, what is the tower to be built, you don't know. So one thing that we are investigating with robots is how we come out with some good coordination with only one person knowing the task. Mm-hmm. In that case, without using overt or linguistic communication. So what we have seen also in robot, that's a very hard problem. Because when you run computational robotic models, then you put your ideas into practice, and you see that by simply predicting the action of the others doesn't work too much. Because then I start predicting you, but so the guy who doesn't know the job has to predict the actions of the other, but it is always one step later. Mm-hmm. It's too late. So it doesn't work very well. So we come out with the idea that the guy who knows the job can also in some sense support the predictive processes of the other or help the other in some sense.
So how would I help my other robot?
Well, one simple example is that I can make my behavior more predictable, such as, I can make my behavior more informative for you, such as I can use my choice of action to letting you understand very well what are my intentions. So you typically try to understand my intentions, but if the uncertainty is too high, I can in some sense help you with the wise choice of actions. That can be very intuitive.
But it could also be a way to test hypotheses about the other. It's not so much making your behavior more predictable. It must be a way to test whether the other has the right model of you.
Absolutely. Yes. That's the idea. So we design...
But it's not the same thing, right?
No. They are related. So in one sense, also in my example, let's call the guy who has the knowledge the leader and the other the follower. So in a sense, the leader can have some uncertainty on what are the models of the follower. Mm-hmm. So of course he can use some actions and monitor the reactions of the other person, just to know what are the good models of what are the models of the other agents. What is he doing?
Right.
And when the leader infers that the follower does not have good models, then he will fail. Then it can, in a sense, try to help the follower. So the two processes are interconnected because by monitoring the process and by always trying to keep track of the uncertainty of the other person, you really can plan helping actions.
Right. But now the thing was interesting that, so we go from action now to interaction.
Yes.
And in your research plan, that's really a very crucial step, right? Because you really seem to think that, or propose that, it's by getting a handle on interaction that you really can get to, let's say, more generalized understanding of social behavior and also cultures.
Yeah.
So how should I see that generalization exactly?
So, well, the point is that I think that for many disciplines, such as the study of language and communication, the natural starting point will be naturalistic joint action. That will be a nice starting point, because now the hypothesis is that the mechanism that we use for interacting with the others in sensorimotor domains, then they provide a scaffold. So they provide some help for developing, let's say, for instance, linguistic communication. The hypothesis, which has been called by Levinson this more interaction engine hypothesis, is that by simply interacting in the external world, we really have some strong pragmatic abilities to infer the action of the other, to do some turn-taking, to do some joint attention, to anticipate the action and the intentions of the others. And this is a strong universal basis also for language communication. So he hypothesizes, for instance, that children use this interaction engine to develop, so to understand and to learn their natural language. And that's exactly a point that we want to make. So we started studying these kind of joint actions. Now we come out with the formulation of the problem in which the two persons happen to solve a joint action optimization process. This joint action optimization process means that it is not only, so I don't have to care only about my action, but also the joint outcome of the action. Because I have to care about the joint action and the joint outcome of our action, which is a joint goal, then I also have to care about you. This is why in some cases, as I told before, I help you, not because I am altruistic. I'm helping you because by helping you, I help the joint goal. So I'm sorry, but I'm not so much altruistic. That's all individualistic. But at the same time, I think that this helping action is really the first primitive form of a communicative action. Because as I told before, I can make my action more observable by you, more predictable by you, more understandable, or more diagnostic for you. Diagnostic here simply means that if you have two hypotheses on what I'm doing, I make my action, let's say, for instance, I exaggerate the movement, such as to make you understand very quickly what is my right intention. So that's diagnostic. But that exaggeration that I do, it's really a form of communication. That's really the bootstrap also of all other forms of communication, including linguistic communication. So the general hypothesis here, this is why I'm interested in this passage from joint action to more complex form of cognition, is that by interacting, because there are some constraints, some joint constraints that we have to fulfill, then in this joint optimization framework, it's quite obvious that I have to do something also for you, for your sake.
Right.
And in our formulation, that means that in addition to having some motor intention, we also have some communicative intention. The communicative intention has a cost, because, for instance, for exaggerating the movement, I pay a cost in terms of biomechanical cost or something. So, such as, for instance, when I am in a noisy pub, I have to over-articulate. Or if you think of the mother is, for example, when the child-directed speech, so you exaggerate, that's done for the sake of the other. Ultimately, we say that's done for the sake of achieving a good joint goal, which is understanding one another. But that's really the first form of motor of communicative intention that I have.
So it's for you, it's really the signaling mechanisms that would allow the bootstrapping of communication and language, right? So, but that's still a project that will be realized in the future.
Yes, but I would say that the important component is always the missing one from the current studies, which is the more pragmatic component of language. So the pragmatics of language, as the early pragmatists which study language know very, very well, So the pragmatic component is prominent because then the grounding of symbols, the grammar, of course, they are hard problems, but the pragmatics, they are the most important part,
right?
Such as, for instance, knowing what requesting means, knowing what telling means, or promising means, or all these joint action and joint attention, turn-taking mechanisms. All of them provide a big scaffolding for the emergence of linguistic communication.
Right. But so I got that. But now, so to finish up, two questions. So you have this really big ambitious program, and in the end, you'll generate the whole of culture from action, which is going to be still a long trajectory. But you're well on your way. But in doing this, what would be Giovanni's law?
Giovanni's law?
Yeah.
Okay. Well, my law will be maybe starting understanding cognition from the primitive equipment of our ancestors. So that would be more an evolutionary route towards the more complex cognitive skills. Well, I can probably give 3 examples that are very simple in the 3 domains that we target now. One is the social domain that we have discussed. So you start from controlling your body, your actions, to controlling our actions, to controlling then your mental states. That's communication. In a sense, communication is really putting something into your brain. Mm-hmm. And then you also develop culture and pedagogy, for instance, for controlling that at a very, very longer time scale. So by developing some culture, the human beings can really control the behavior of many people over millennia, probably, and also by pedagogy. So that's in the social domain. You can see this also in the control of the external world on this environmental scaffolding or on the environmental shaping. So we start from the control of our body to the control maybe of the reality of our peripersonal space with some objects. And then you start controlling tools, for instance, for doing more complex actions. And but then tools, you have also to build tools. Maybe at some point you build the city of Barcelona. So then in a sense you extend the boundaries of your control from the control of your body to the control of the whole environment. We humans really modify our environment very much, such that then they support much better our cognition. So that's another story, not only in the social domain, also in the environmental domain. Right. The third and last one is in the more thought domain or the cognitive control domain. So you just start from controlling your action, and then you end up in some way by controlling your thought processes and by controlling your cognition over long time scales. For instance, one example that I do, let's imagine I want to become a prominent scientist, which apparently doesn't happen right now. So I have to control my behavior for 20 years maybe. So the way I do that is by cognitive control, in a sense, by setting some goal states into my mind, then control my behavior on longer time scales. Mm-hmm. Then again, you have this control of the body, or the control of my short-term actions that become the control of my entire life. Mm-hmm. And so I have given 3 examples of how this research program, I would say, will start from very simple sensorimotor abilities to very, very complex abilities that cross the boundaries of many disciplines, sociology on the one hand, and let's say architecture on the other hand, or maybe the study of consciousness on the other end. So, of course,
and you have even integrated it in your own career planning.
Yeah, of course.
So the very last question then is prediction. So if we come back then 5 years from now as a famous scientist to the summer school again, so what's the one prediction we can test on you by then? So what's the one prediction you would like to make today that you feel very strongly about, and we can ask you about 5 years from now?
Okay, so about the future of this field or about
your research program?
Okay, so about my research program, I think I've elucidated the principal, my key goal, which is understanding higher cognition, how higher cognition is based on sensorimotor and predictive abilities. So the prediction is that at least we will have some nice demonstration in these 3 fields that I've mentioned before, much stronger demonstration than the ones that we have now. And from that, we can really try to build an understanding of how the brain implements higher cognitive skills. So all right. At least one demonstration for each of the 3 fields. That's
very good. So, Giovanni Pezzulo, thank you very much for this conversation.
Thank you, Paul.
The CSN podcast was produced by the Convergent Science Network of Biomimetics and Biohybrid Systems, a project funded by the European 7th Research Framework Programme. For more interviews, recorded lectures, or upcoming conferences in the field of biomimetics and biohybrid systems, go to csnnetwork.eu. And thank you for listening.